Okay, so we're going to have a little look at activation energy because it's something we've talked about a lot to do with catalysts, so what it actually is, how we represent it, and what that actually means in terms of rate of reaction a little bit. There may be some ideas that we cover in this bit, like enthalpy, that come into later topics like energetics. Don't panic if you don't understand them too much, it's just a mini introduction of those things. So, activation energy is the amount of energy required to break the bonds in reactants so that the reaction can begin. So note here, you are having to put energy in to break bonds apart. So this makes sense. If you imagine you've got your bond, you've got to put energy in to pull it to pieces. So breaking bonds requires energy. And we tend to show this on an energy or an enthalpy level diagram. Now, enthalpy we'll cover more when we get to energetics, but in basic terms, think about it as the amount of energy in the chemical. Okay, so this is actual energy trapped in the chemical in the bonds. So in our energy or enthalpy level diagram, we have energy on our y-axis and reaction progress on our x-axis. And they tend to be sketch graphs, okay, so you could be asked to sketch these. And over here we have our reactants. Obviously, if you know your chemicals when you're doing this, you could write the real reactants in. Down here is our products. So this is what we make at the end of our reaction. And as you can see, in this case, our products are lower in energy than our reactants. Energy has come out of our reaction. So we would call this bit, this change in energy here, enthalpy change, okay, which we frequently represent as delta H. Like I said, we'll do a lot more of this when we look at energetics later in year 10, but just an idea, this change in energy is how much energy has come out of the chemical in this case, because we've gone down. This line up here is when all our bonds are broken. So this represents we have pulled all of our atoms apart, ready to form into our products. So that means our difference in energy here, the difference between our reactants and our broken bonds, this is our activation energy. Okay, this is the energy that has to be put in to make the reaction happen. And quite often we represent this as a big E and a little a, energy of activation. Should also add that the energy coming out here, this enthalpy change, it tends to be released as heat. You know this, we've encountered heat coming out of reactions before. So this diagram would be for an exothermic reaction, heat coming out, because our arrow is going downwards. So what does this mean in terms of our catalysts? So when we say catalysts offer an alternative route with a lower activation energy, what this looks like on our enthalpy level diagrams, we've still got energy on our y-axis, reaction progress on our x-axis, our reactants and our products, they still have the same delta H going on here. So the energy change hasn't moved at all because we're still going from the same reactants to the same products. So that energy change is going to be the same in the chemical. What is different is our activation energy. So as you can see, this was our original bonds broken activation energy. And this is our new energy, activation energy that's required. So with the catalyst, obviously less energy is required to break the bonds, so it's lower on our energy scale. So if we want our reaction to go this way, our activation energy without a catalyst, you need far more energy than if you are using the catalyst. Okay, so it's a smaller energy, so more particles are able to access this level of energy. Sometimes when we do a sketch diagram, I'm going to do a very rough sketch diagram, this can be shown as a curve. So you could end up with a graph that looks a little bit more like this. So this would be our reactant line, this would be our products line, and they would show it like this as a curve, because the chemicals don't really stay in these two states, they pass through it. Obviously once the bonds are broken, they start turning into products. So it could be shown as a curve, and then the catalyst one would be shown as a lower curve. So our red line would be with our catalyst, and our pencil line would be our normal reaction. So in the same way, if it's a curve, our activation energy is shown between our reactant line and the top of the curve. So that would be our differences in activation energy. For those of you who are still a little bit, why does lowering the activation energy make the rate of reaction go faster? You can show this on a graph. So in this case, our energy is on the x-axis, and this is our number of particles, our number of reactant particles that are in our reaction. And as you can see, there's a curve showing the energy of each particle, because we're plotting the number of particles with each energy. Some have very low energy, some have very high energy, but the vast majority of particles have this energy here, so that's why we reach the peak. So if we have our reactants and they're spread over this kind of distribution of energy, if we imagine our normal reaction, which we can show with a green line, our activation energy, let's say, could be here. We require this much energy for the reaction to happen. So that means when a collision happens, only particles with energy above this green line, this little section here, are capable of reacting. So all of these particles can collide many, many times, but will never react because they're not over the activation energy. So we've only got this little section of particles here that are available for reaction when they collide. Now, obviously, if we put our catalyst in, so if we have our catalyst, it offers the alternative route with a lower activation energy. So its line, its activation energy, is going to be further down this direction. So this could be our catalyst activation energy. So now, obviously, anything over this line can react. So not only have we got the green particles that are capable of reacting, we've now added all of these particles here that can also react when they collide. So there's a greater chance of our collisions being one of these particles that are over the activation energy, and therefore you're going to get a higher rate of reaction because you're going to have more successful collisions per second.